Okay, so let's begin. So remember from the previous class that we've been interested in solving the Laplace equation, right? And what we had done last class was to solve this in 2 dimensions. On a plane, we solved the Laplace equation and found all of the solutions of the Laplace equations, or in particular, all of the polynomial solutions of the Laplace equation, right? And we had done that by noticing that in 2 dimensions, solving the Laplace equation is particularly easy if you know some complex analysis. It's to just write down all of the polynomial analytic functions, right? So we wrote down these functions in 2 dimensions. In 2 dimensions, we wrote down rho to the L e to the plus minus I alpha, and we noted that these solved the Laplace equation, right? And then remember that we had done a counting. So here at degree L of the homogeneous polynomial, there are 2 solutions. 2 solutions at every degree L greater than or equal to 1. L equal to 0, remember there's only one solution, which is the constant. One independent solution, 2 independent. Okay. So in 2 dimensions, at every L, at every degree, there are 2 solutions, L greater than or equal to 1. Now in 3 dimensions, we counted by Bose counting. We counted that there are 2L plus 1 linearly independent solutions at every L. Right? But I had noted immediately that these 2L plus 1 linearly independent solutions are the spherical harmonics, right? But we hadn't derived them. These are R to the L times the spherical harmonics. And I had promised you last time that we will derive this today, okay? So one can actually do this in a far more general way. To do this in an arbitrary number of dimensions, you can write down the spherical harmonics in an arbitrary number of dimensions, and there is a very systematic way of studying them, and many things about them become natural in this far more systematic way of doing it. But we will take a more pragmatic approach, and we'll only be interested in the 3-dimensional spherical harmonics, the spherical harmonics on the 2-sphere, on S2, okay? And there exists a certain method, a very simple method to derive these d equal to 3 spherical harmonics, which is called the herglotz generating function. This method, using this generating function, can't quite be generalized to an arbitrary number of dimensions due to a set of reasons, but in d equal to 3 it works well, and that's the place we'll be interested in. That's the dimension we'll be interested in. Okay, great. So let's begin. Okay, let's begin by considering a very simple looking function that we're all familiar with, which is e to the h dot r, where h is some constant vector. Okay, now let's try to understand how the Laplacian acts on e to the h dot r. I hope you can all see this, right? Yeah, great. Okay, let's act the Laplacian on e to the h dot r. So what do we get? The Laplacian is divergence gradient of e to the h dot r. When the gradient acts on e to the h dot r, which is some scalar function, it gives you h vector times e to the h dot r. Okay, so that seems to imply that Laplacian acting on e to the h dot r is equal to, now divergence of a vector times a scalar is equal to divergence of the vector times the scalar, but h is a constant, so divergence of h vanishes. And then you only need to do h dot grad of e to the h dot r, which is h. So this becomes h squared e to the h dot r. Oh, you can't see that? What we get is grad squared e to the h dot r is h squared e to the h dot r. Okay? So now you would say, oh well, for e to the h dot r to be a solution of the Laplace equation, we require h squared to be 0, right? Therefore, e to the h dot r solves grad squared phi equal to 0 if h squared equal to 0. Okay. Now you look at this and say, oh well, this is trivial because it will only give you the trivial solution, because if h squared is equal to 0, h squared, remember, is just hx squared plus hy squared plus hz squared, all three of which are positive numbers. And so h squared equal to 0 would imply h equal to 0. And e to the h dot r when h is 0 is just 1, and 1 is obviously a solution of the Laplace equation, so we've learned nothing new. But notice that I never told you where h is valued, right? So if you take h to be complex, h squared equal to 0 is not so constraining, right? It still leaves a full set of solutions. Now that's what we will do, okay? So e to the h dot r still solves grad squared phi equal to 0 if h squared equal to 0, but h squared equal to 0 does not imply h vector equal to 0 if components hx, hy, hz belong to the complex numbers. And that observation will be crucial to us. Okay? Is it fine? Cool. Now let's begin by parametrizing. So let's write down the solution by parametrizing h squared, h in such a way that h squared equal to 0 is obvious. Now note that h squared is just hx squared plus hy squared. Thanks. So now note that h squared is just hx squared plus hy squared plus hz squared, right? Now this I can parameterize, or this I can rewrite as hx plus ihy times hx minus ihy. You'll see why I'm doing this, plus hz squared, right? That's clear, right? Because hx plus hy times its complex conjugate is just hx squared plus hy squared plus hz squared. Okay. Now, one way to make this equation natural is to parameterize it as follows. Don't worry about the subscripts, the choice of the subscripts for the symbols. They'll become natural in one moment. But xi is some arbitrary symbol. But notice that this parameterization immediately solves that h squared equal to 0, because this will give you h xi minus squared here, minus xi plus squared. So this is minus xi plus whole squared, plus xi minus xi plus whole squared, which vanishes. Okay. So now we have some parameterization for hx, hy, and hz. Now all we need to do is expand e to the h dot r to find the solutions, okay, which let's do. Maybe I should write this here. Before expanding, let me just do that. Can you see this? Yes. E to the h dot r. Maybe I should not write that. E to the h dot r is equal to summation L equal to 0 to infinity h dot r to the L over L factorial. So we need h dot r to the L. So let's simplify h dot r first. H dot r is equal to hx x plus hy y plus hz z. Right? Yeah. And then we can do, let me find another chalk. This will be equal to, since hx plus hihy is I minus squared, I want to write it like that. This will be half hx plus ihy times x minus iy plus half hx minus ihy times x plus iy plus hz times z. Okay. Now, remember a few things about spherical coordinates. X, maybe I should write this elsewhere. Maybe I can write this here if you can see it. Yeah. So remember that x is r sine theta cos phi, y is r sine theta sine phi, and z is r cos theta. In which case x plus iy is r sine theta into cos phi plus I sine phi. And cos phi plus I sine phi is e to the I phi. So this becomes half xi minus squared, right? Xi minus squared is what I parameterized it as, times r sine theta e to the I phi. This, oh, you see that hx with x gives you xhx plus hxx. So that's 2. So I put a half to get rid of that 2. Same thing with the other terms. I into minus I plus 1, minus I into I plus 1. And the cross terms vanish, which is why these minus signs are there. Okay, and now you see why I put the this is a minus sign, right? Now you see why I put the minus sign. This minus sign is because of that minus sign. I could have parameterized it with some other symbols if you like. Minus half xi plus squared sine theta r sine theta times e to the I phi plus hz, which we parameterized as xi plus xi minus times r cos theta. It's warm in here. Could you? Yeah. Great. Okay. Now let's simplify this a bit further. Or maybe let me write h dot r to the L. H dot r to the L will be r by 2 to the L times xi minus sine theta e to the minus I phi minus xi plus squared, I suppose, squared sine theta e to the I phi plus xi minus cos theta to the L. I took a half out, so that puts a 2 there. Cool. Go. So now we need to simplify this before expanding it out. I want to expand it out in powers of xi minus and xi plus, because those will be the, remember that h was the parameter in which the generating function works. Okay, this I probably didn't tell you. E to the h dot r will expand in powers of components of h. Okay, the components of h is what is generating your spherical harmonics. Okay, as we'll see in a moment. So I want to sort of clean this up. So in order to do that, let me take, you'll see why I'm doing this, xi plus squared e to the I phi over 2 sine theta. You might think why I took the sine theta in the denominator. You'll see in a moment why. Because you'll get a sine squared theta here and you can use a trigonometric identity. Let's see. So you get xi minus over xi plus. Yeah, sine theta e to the minus I phi squared minus that xi plus squared is taken out, e to the I phi is taken out, sine phi is in the sine theta is in the denominator, so this gives you sine squared theta plus 2 xi plus, I took a xi plus squared out, okay, so that makes this a xi minus over xi plus. I took a sine theta in the denominator, which goes up in the numerator. I took an e to the I phi, so that gives you an e to the I phi in the e to the minus I phi, and a cos theta. Okay. Now you can take things outside. So now that we can write as h dot r to the L equal to r xi plus squared e to the I phi over r sine theta, sorry, 2 sine theta to the L times, is there a way you can see both of this at the same time? Let me see. Probably not. Yeah. Now you notice that I can make this a xi minus by xi plus sine theta e to the minus I phi plus cos theta whole squared, in which case the cross term is already here. So let me write xi minus over xi plus sine theta e to the minus I phi plus cos theta whole squared. Now let's see. Square of the first term is already here. 2 times first term times second term is here, if I did this correctly, right? Third term will give you cos squared theta, but cos squared theta is 1 minus sine squared theta. But minus sine squared theta is already here, so all I need to do is minus 1 to the L. Now some of you who know spherical harmonics might already start seeing that the x squared minus 1 to the L is emerging, or cos squared minus 1 to the L emerging, right? Okay. Now a couple more steps. Remember that these are all simplifications to get it into like a standard form. So a couple more steps to simplify this a bit further. So you can write this as r xi plus squared e to the I phi over 2 sine theta. Now I can Taylor expand this, okay? So let's treat this as a function that looks like this. Maybe let me write it here. F of x, the function here is x squared minus 1 to the L, right? Where I'm treating this whole thing as x, okay? Okay? And so then f of x plus delta, maybe I should call this y. Let me call this y to avoid confusion, okay? F of x plus delta by Taylor's theorem is just e to the delta d dx on f of x, which is simply summation m equal to 0 to infinity, say n equal to 0 to infinity, delta to the n over n factorial d dx to the n acting on f of x. Now notice that f of x here is at max 2L degree, right? So the highest power in f of x is x to the 2L, which means this sum will truncate. This sum will truncate to summation n equal to 0 to 2L, already a good sign, there are 2L plus 1 things, delta to the n over n factorial d dx to the n f of x. Okay. Now here I will consider x is equal to cos theta, this cos theta, and delta is equal to xi minus over xi plus sine theta e to the minus I phi. Now notice that I don't intend here to connote that delta is some small number and x is some big number or anything like that. This is just notation for using this Taylor expansion. Since this Taylor expansion has only a finite number of terms, we don't need to worry about convergence and all that, and why delta has to be small and all that. But delta is not small, just some notation. Maybe I should not call it delta. What would you like me call it? Let me see. Maybe xi? No, not xi. Maybe eta. Say eta. 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 Okay? So eta is that. Okay? So then here I can simply write this sum, right? We can write summation n equal to 0 to 2l xi minus sine theta e to the minus I phi to the L time divided by L factorial, 1 by L factorial. Sorry, to the n times dd cos theta to the n times cos squared theta minus 1 to the n. Okay? Now, to bring it into a more familiar form, this is what we've been doing for a while, I want this sum to go from minus L to L, right? Because in quantum mechanics, for example, you have these 2L plus 1. If you're doing representation theory, you have 2L plus 1 states, and the states go from j equal to minus m to j equal to plus m. Okay, and that's the usual thing, and that's what I want to reproduce. So I want this sum to go from minus m to minus L to L. So let me define. Maybe I should go sideways. Let me define n m as, give me a moment, n maybe as m plus L, m minus L maybe. Okay. So then this thing is equal to r xi plus squared e to the I phi over 2 sine theta to the L. We don't need that. Summation. The m here for n equal to 0, m is just 0 plus L, which is L. So m equal to 0, L. And for 2L, no, this is not what I want. I think I need this. No. This is what I need. N equal to L minus M. Okay. Which means M is L minus N. So here it's L, here it's minus L. Okay. And xi minus over xi plus sine theta e to the minus I phi. That's right. Yes, indeed. L minus M. 1 by n is again L minus M factorial dd cos theta to the L minus m cos squared theta minus 1 to the L. Okay, great. Now a summation going from L to minus L is the same as summation going from minus L to L, right? Because it's just changing the order in which you're doing the sum, that doesn't matter. Okay, so we have all the ingredients we need. Now let's just put it into the generating function. So e to the h dot r becomes summation L equal to 0 to infinity summation m equal to minus L to L 1 by L factorial. This is from the sum in the expansion of the exponent times r xi plus squared e to the I phi over 2 sin theta to the L times xi minus over xi plus sin theta to the minus I phi to the L minus m 1 by L minus m factorial dd cos theta to the L minus m cos squared theta minus 1 to the L. Okay. So now we just need to identify the spherical harmonics, right? Now, by convention, the spherical harmonics are normalized such that they're orthonormal. If you do an orthonormality integral, you take an inner product of YLMs, they give you 1. Okay, so there'll be some numbers, there'll be some coefficients which I'll just write down. Okay, which don't really matter. I mean, which will start mattering only when you start doing these orthonormality integrals. And you can do those integrals and fix them. Once you have a generating function, doing an orthonormality integral of YLM is basically doing an integral of e to the h dot r, which we know how to do, right? So I'll just write down those numbers and not worry about them. If you're interested in fixing those numbers, I'll encourage you to do the orthonormality integrals and check more properties of the spherical harmonics and so on, which I'll probably try to put in my notes. Okay, yeah, so let me write down the convention. So e to the h dot r, I hope I get this correct, you write as summation L equal to 0 to infinity, summation m equal to minus L to L, root 2L plus 1 by 4 pi. This factor is what gets rid of a number in the orthonormality integral such that it is actually properly orthonormal, times xi plus, what is the power of xi plus? 2L minus L plus m, so that is L plus m, xi minus to the L minus m, and they're also normalized such that you have these square roots. I'll write down the square roots. Another way you can check this is by putting m equal to 0, in which case you must really get the Legendre polynomials, which most of you must be familiar with from a first course in electromagnetism, where you're solving this azimuthally symmetric problem in spherical geometry. And you can check that these YLMs go to that PLs, okay, with these normalizations. So you put L plus m factorial, L minus m factorial, okay, times YLM, theta comma phi. Okay, which means I'm exactly at the end of the board. I think this is the result we wanted. So YLM of theta comma phi is equal to, let's compare, and yeah, that's correct. So, and an r to the L, sorry, r to the L. Okay, so the YLM is the r to the L taken out. It's just a function of theta and phi. Is what? E to the I phi L, e to the minus I phi L. So those two e to the I phi's cancel, but you have an e to the plus I m phi. So e to the I m phi Okay. What else do you have? You have a sine theta to the L, but then you have a sine theta to the L here as well. So it's just a sine theta to the minus M. Maybe I should write the constant factors first. So you'll have a factor of 4 pi to the 4 pi over 2L plus 1 to get rid of that. Okay, so that factor is done. So for this factor, you have an L minus M factorial here. So what you really need here is an L plus M factorial over L minus M factorial. So that gets rid of the factorials. So we're done with the factorial. We'll come to this. Okay. Now let's look at this. R is gone. This is gone. E to the I phi, we just argued those two go away. So you'll get an e to the I m phi sine theta to the minus m. Okay. So you have that 2 left. We'll come to that 2. Okay. Let me write this term down. d cos theta to the L minus m cos squared theta minus 1 to the L over 2 to the L from here and the L factorial from there. And that's how one usually writes the spherical harmonics. Actually, usually people write it as sine theta to the m with a minus 1 to the m. That's a trivial, well, not trivial, but that's sort of a simple trick, not trick, but you can do a simple thing here. You can just basically you need to realize that things, whatever I've done in some steps that I've done, you will realize that YLM is symmetric when m goes to minus m, theta goes to minus theta, phi goes to minus phi. Okay, which must also be physically obvious to you. So once you do that, YLMs remain the same YLMs, they're symmetric. So you can just do that m going to minus m, theta going to minus theta, phi going to minus phi here, and you'll get the typical way in which, for example, Arfken or Griffiths or Schwinger or all these people write the spherical harmonics. Okay. Okay. So let's stop here. Today was a short lecture. I just wanted to be done with the spherical harmonics. So we're sort of done with solving the Laplace equation because we solved it in 2D earlier. Remember, which gave us rho to the L e to the plus minus I L phi, and we just did 3D and we got R to the L times spherical harmonics. Right, and note also that there are 2L plus 1 of these which fits our counting. So basically that means we have all the polynomial solutions of the Laplace equation. Okay, so we've basically solved the Laplace equation in 2D and 3D. 1D is trivial. Okay, so till 3D we have solved the Laplace equation. Next class we'll want to solve the Helmholtz equation. Okay, and as I said in my introduction, the Helmholtz equation comes up when you're solving wave equations and so on. So we're really looking towards radiation. We want to be able to solve radiation problems for which we want to solve these Helmholtz equations. And eventually you'll start putting sources on the RHS of all these equations. And to solve those sourced equations, we'll need green functions of all these equations of Laplace, Helmholtz, and so on, which is what we'll do after that. Okay. So before ending, let me give you some names of all these things. So e to the h dot r is what I called the herglotz generating function. And h, the vector h, is called the herglotz vector. When parameterized in the way we did, it gives you the spherical harmonics in this convention. Okay. Okay. Did I have anything else to say? Let's see. Yes. So I'll also put this in the notes. I'd encourage you to take the m equal to 0 part of this YLMs and see that they are the PLMs. So by the way, I forgot to say that this, what we have derived here, is the Rodriguez formula of the spherical harmonics. And by putting m equal to 0, you can get the Rodriguez formula for the Legendre polynomials and check all of the recursion relations that you might have derived in an earlier course. And if you take the e to the I m phi out, whatever is remaining is also called the associated Legendre polynomial, the PLMs. You can look up any book for the conventions and write them down. Okay. So basically, what we have done today is to solve the Laplace equation in 3 dimensions. Okay, in R3, which gave the polynomial solutions of the Laplace equation. So R to the L by Lm. And one last thing which I forgot to say now is the following. You might have noticed, some of you might have noticed, that we only got R to the L by Lm as the solution, okay? But you might ask, well, if you put m equal to 0, that's R to the L PL. But I remember from Griffiths that it's not just R to the L PL, there is also 1 by R to the L plus 1 PL, right? But that is something that I wouldn't call a solution, right, in R3, because I'm looking for a solution in R3, which means I need something that's regular in all of R3. But 1 by R to the L plus 1 PL, remember, has a singularity at R equal to 0. So I wouldn't really count that as a solution, okay? But you can meaningfully well ask that if you remember, if you take R3 minus 0, R3 minus the point at 0, then what are the solutions of the Laplace equation? Then you would have to include this 1 by R to the L plus 1 PL, okay? But there is a very neat trick to get that 1 by R to the L plus 1, which I'll put in my notes, and you can also read about it in Schwinger. Okay, the neat trick is inversion. Okay, so the Laplace equation is symmetric under. Let me see. Okay, maybe I should not write this down. I might make a mistake. So let me just say that if f is a solution of the Laplace equation, there is some non-trivial way to do an inversion such that you do an inversion of the arguments, and that is also a solution of the Laplace equation. I'll detail this probably the next time, okay, before we start. So basically, if R to the L is a solution, you can show that 1 by R to the L plus 1 has to be a solution. Okay, so that way you can get 1 by R to the L plus 1. I won't belabor on that now, but you can probably you can go home and show this, that if R to the L is a solution, 1 by R to the L plus 1 is a solution. In which case we basically have everything that Griffiths has: R to the L by Lm and 1 by R to the L plus 1 by Lm. Okay. Okay, so that's where I'll stop.